The strangest introduction to the video that we've had, but there we go. It's fine, not a problem. So what's up, you scholars of enlightenment? NASA's Hubble Space Telescope has established an extraordinary new benchmark, detecting the light from a star that existed within the first billion years after the universe's birth in the Big Bang, and the furthest individual star ever seen to date. The light took 12.9 billion years to reach us. The star is named Earendel, the morning star, and it existed when the universe was about 1 billion years old, or only about 7% of its current age, at a time that astronomers refer to as redshift 6.2. So to help me unravel this amazing discovery, which is now in the paper Nature, we have another superb special guest, Dr. Michelle Thaller. So Dr. Thaller, welcome to the podcast. Thaler or Thaller? Am I butchering your name?
Thaller's good. Yeah, I answered anything, but Thaller's good. Yeah.
Excellent. So Dr. Thaller is an astrophysicist with over 2 decades of science communication experience, and her research involves the life cycles of stars, and she's worked at the Jet Propulsion Laboratory and Goddard Space Flight Center. She's also appeared on many television science programs, including How the Universe Works and Space's Deepest Secrets. And she's now the NASA Assistant Director of Science Communication, which sounds like an incredible job. You said to me one thing before we get started, that you had an engagement this week where you had to dress up as a triceratops. Can you tell us something about that? Before we get into the serious science, yes. I want to hear about this.
So yes, there's an amazing result that's coming out on Wednesday, and unfortunately the press release is still embargoed for 2 days. But it's something that involves the last day of the dinosaurs and the idea of impacts in dinosaurs. And there's going to be a big press briefing, and I'm going to be on the panel of experts. And I don't intend to wear my costume, but in the opening reception where we're having like coffee and cookies, I have an inflatable triceratops costume. It's wonderful. So, I mean, it's got this big triceratops head, and then it's huge. I mean, it kind of drags behind me. And you put your feet in the front legs. And so I'm going to show up for a little while and have a dinosaur be at this reception. So yeah.
Any more details about what that finding is, or are you said embargoed? So
well, like I said, it's the actual press release is embargoed. I actually saw it just today. We gave BBC the information, so they should be getting all their stuff ready for Wednesday. So it's an amazing result, but that's, I mean, aside from it having to do with dinosaurs and impacts, that's all I'm going to say until Wednesday. I'm sorry.
Okay, I'm not going to push you any further, because I know how these things go. So I will ask you one other cheeky question before we start, though, because the Hubble Space Telescope, everyone loves the Hubble Space Telescope. Everyone loves their deep field screensavers, or at least I do. It's been my screensaver for absolutely ages in different forms. However, Hubble's long-term successor, James Webb Space Telescope, is preparing to take science. So is the timing of this release, and obviously you work in science communication with NASA, is the timing entirely coincidental? Or is this one last hurrah for Hubble and a very nice handing over of the torch, handing over of the baton for James Webb?
Oh, well, no, actually, nothing like that. It is entirely coincidental. I mean, this is a recent result that came out from a paper, a wonderful young man who's just getting his doctorate.
Yeah.
And that's kind of nice to have a paper in Nature when you're, a doctoral candidate. So there wasn't any particular timing in terms of a handoff. We actually hope these two telescopes are going to work together for quite a while, because they see very different parts of the electromagnetic spectrum. So Hubble sees mainly visible light. It sees a little bit into ultraviolet, a little bit into infrared. But then Webb is all past Hubble, all the way into infrared. And so the two telescopes don't look at the same type of sky at all.
Yeah.
And so the thing with Hubble is that because there's no longer the space shuttle, we can't get astronauts up to service it anymore. Yeah. And so the last servicing was in 2009, and now we just run it until it breaks. I mean, seriously, that's the plan. I mean, it doesn't sound like a very specific plan, but we won't be able to service it again. But as long as it's operational, it's still performing incredible science. In fact, we just had the results of the latest call for proposals. Every year, people write in and say, please let me use Hubble for a few seconds. Like, I want to look at this.
Yeah.
And Hubble is actually as oversubscribed as it always has been. So it's still a very, very useful telescope. But yeah, I mean, James Webb, wow. I mean, I can't believe how well it went. I could barely, I've been worrying about this thing for 15 years, and
Yeah.
I'm not exaggerating. And
I
to
was
see
saying
it,
when I was talking to Stephanie Millam that I've been hearing about this damn thing when I was doing undergrad lectures 20 years ago. They were like, "Oh, James Webb will be coming in a few years," and I was like, "Wow, that sounds like an amazing telescope." And it's been
uh,
2 years, 2 years, 2 years, 2 years, 2 years for the last 20 years or so.
yeah.
And then we had the incident before Christmas. We thought, oh no, this is going to be another postponement, and then it went off at Christmas because um, obviously it did after all that time. But it was an amazing journey to even get to that point. So to then see it go so well must have been very very impactful and very emotional for the people involved.
It was extremely emotional. And I mean, I had lost sleep over things. I mean, so my husband was an engineer that worked on James Webb Space Telescope on a lot of the very fine focusing part of it. The part that you can basically move the mirrors by not too many atoms, to get them perfectly focused. I mean, about 1/20,000th the diameter of a human hair. I mean, it's unbelievable.
Yeah, it is.
For one thing, how do you do that? How do you even measure that? That was the kind of stuff that he did. And so I mean, to have this be sort of a family member that was talked about over dinner, lying awake at night going, oh my God, there's 317 single point failures, and but then to have this thing work, wow. I mean,
my friend was he does some work on Mars rovers, and they talk about the 8 minutes of terror or whatever it is when the thing drops into the atmosphere, and he was saying this is basically a year of terror where it gets out there, 6 months to unfurl everything, so many single point failures that can happen, and amazingly they all seem to have gone perfectly well and indeed outstripped expectations. I'm hearing on
That's right. So, I mean, images are now coming in. We're getting all the different instruments commissioned, and all the different little fine focusing and fine adjustments that are involved with those. And the big release of the beautiful. We want to have many different gorgeous images for people to look at for the big opening release. That'll be in July. Amazing. And there'll be pictures of planets in our solar system, of beautiful nebulas, of distant galaxies, all of that. And but the stuff is already coming in, and just judging from I mean, one of the things that astronomers talk about, like things like the dark current, the noise in the background is better than we hoped it would be. The focusing is just spot on, perfect. I mean, it almost seems unbelievable. We're all kind of waiting for the other shoe to drop because I mean, this has just gone perfectly, and I'll touch wood or something while I do that.
Well, even just as a tech demo to show that you can make an unfolding telescope in space. I mean, the implications that has for future missions, even larger missions going beyond James Webb as well. It's just a phenomenal thing that they've achieved, and absolutely superb science and engineering. So I take my hat off to them.
Yeah, I mean, I think they'll do that again. I mean, it's funny. I guess I'm a little bit of a conservative scientist when it comes to engineering. I was at JPL when they were talking about the Curiosity rover. This was of course Curiosity's been operational for 10 years almost. And when they were talking about, oh yeah, we're gonna first we'll parachute it, then we'll cut the parachute off, then we'll have retro rockets, then we'll have a sky crane on wires and lower this thing down. And I remember being at a seminar at JPL and just saying, well, what the fuck? I mean, there's no way that's gonna work. There's no way. And of course, it worked perfectly twice. Yeah. So I mean, obviously, we learned a lot about how to build one of these unfoldable telescopes. While we worked on Webb, while we figured out what the problems were. And so, I mean, I think that knowledge base is now there, and that can move forward. So, I think that the next time we'll do it even better. I hope.
Fingers crossed.
More smoothly. Yeah.
So moving on to this specific finding that was the sort of all over the news this week. What is the big amazing new discovery here? This is the furthest away single star that's ever been observed. Is that correct?
Well, at the very least, a star system. Yeah, I mean, we see this as a very, very tiny dot, and we really it's so small it can't be anything as big as like a big star cluster.
Yeah.
So we think that it's at least, if it's not a single star, it might be a binary
Yeah.
star or a star system.
Yeah.
We can't exactly say that it's one. It could be two stars going around each other, but yeah, this is small, and so it has to be, a very big, very bright, and very, very early type star, a star that existed, like you said, when the universe was less than a billion years old. And that's amazing. And there's no way we should have been able to see a star that far away.
Yeah.
And so it's this incredible coincidence of using these natural telescopes, which are gravitational lenses. And that's amazing to see. I mean, I guess we could sort of start from the beginning that there's a cluster of galaxies that's much closer to us. The cluster of galaxies is, I looked this up. I think it's about on the order.
I've got a little. I can zoom over to here and help you out. I think. Yeah. We've got all the things you need around here. We can help you out a little bit.
Yeah. So you see that exactly how it is. So there's a bunch of galaxies closer to us, and we see them as they were about 5 billion years ago. And then that's right, that nice little glare. But then way behind them, way in the background, is a galaxy that contains this star. And that galaxy's light is being actually warped around the galaxy cluster, because the galaxy cluster, I mean, it's amazing. Einstein said 100 years ago that gravity really is a bending of space and time. And everyone's like, oh yeah, that sounds good. I mean, there's nothing like that we experience in our everyday lives. But then there's so much mass in this cluster of galaxies that it's doing it right in front of our eyes. I mean, the universe itself is bending light, and just sort of coincidentally, the way it's being bent, this little star is lined up so that its light is actually amplified. It's actually sort of focused, almost like I said, the space telescope,
like a sort of convex lens, kind of.
Yeah. Yeah, that's right. So it just, I mean, this star, like I said, again, coincidentally, just happened to line up so that it got amplified by thousands of times brighter than it should have been. And also, luckily for us, this star is very massive. It's probably at least 50 times the mass of the sun, and so naturally, it's probably about 1 million times as bright as the sun. And then you get amplified by thousands of more times. So I mean, the only reason we see this is that it is billions of times brighter than it should have been. Well, I mean, 1 million times as bright as the sun, and then thousands of times amplified. So it's a bright thing.
So when we look at this diagram, I think we can sort of zoom in on another one that they have in the paper. Is there a particular reason why? So the star Earendel here. Is there a particular reason why this one is so amplified? Is it to do with the sort of distribution of that galaxy cluster? So there's certain points where exact points that get amplified even more. Is that the sort of thing that we're
driving absolutely. So people probably haven't heard the term caustic rays, but there's something that you see all the time in the bottom of a swimming pool or in the ocean. That when you see light being reflected through the waves onto, let's say the bottom of the swimming pool, you'll notice there are sort of lines that are really bright, really, really bright lines, and that's where things are being focused even more intensely, due to the lensing of the water.
So due to all the peaks and troughs in the surface of the water, there's various areas that are more magnified than others. Is that
absolutely
okay?
Yep. And so this gravitational lens has the same thing. It's got sort of a ripple-like structure, if you think about it. Yeah. And so this star just happens to line up with one of those peaks that's really focusing the light more than it should. So there's a reason why the whole galaxy, and sometimes in gravitational lensing, you do see the entire galaxy lensed. Yeah. And distorted and made into weird smears. It's amazing to think that's what you really would see on the sky if you had eyes as sensitive as Hubble. This is not computer generated, right? Yeah. We don't take images of galaxies and smear them out to show you where the lens is. That's really in the sky. Yeah. That's what it looks like. Yeah. And so there's and you see actually that there's a magnification line. There's a dotted line in the diagram you've got, and that's where we think that caustic ray is, basically the really intense magnification. Yeah. And so you have Earendel in the middle. And then you have two images on either side of probably the same star cluster. because they're actually mirrored. In one case, there's one of my favorite gravitational lenses. It sounds like a strange thing to say. Good dinner conversation. One of my favorite gravitational lenses. There's this galaxy that's actually mirror imaged on itself, and it looks kind of like this monster with evil eyes. Because it's wonderful. I can send you a picture.
Can we look for that one maybe? What's it called there?
I see. There are all these telephone numbers, and I mean, it might be part of the Able cluster, but let's find it later.
We'll find it later.
Yeah, but at any rate, so Earendel, is coming through, and so one of the things we're really keen to observe, probably with the Webb telescope as opposed to the Hubble, is something called population 3 stars.
Yeah.
And population 3 stars are sort of a holy grail to astronomers. And I'm actually an astronomer that specializes in massive stars, so I'm like, ooh. But all of the stars. There we go. Another diagram. Population 3 stars. So. And is that the Spitzer result you have of the possible background?
I believe this is Spitzer. Yeah, when I was looking for the pictures.
I mean, some people can recognize like a type of car going by, or there's women that can recognize like what year Chanel suit that was. It's like, oh yeah, that's a Spitzer image. I remember that one. So
good, I like it.
So stars today, of course, like the sun, they were part of subsequent generations of stars after the first ones blew up.
Yeah.
And so we have all of this wonderful, the stuff that astronomers call metals, which is really fun because everything that's not hydrogen or helium is a metal. Most people don't think of neon as a metal, but astronomers call it that. All of this stuff that had to be made inside stars that then exploded. The population 3 stars didn't have any of that. They formed out of just hydrogen and helium. Yeah. And because of that, they probably worked very differently.
Yeah.
Because the atmospheres stored energy differently. My guess is they were huge. They might have been even thousands of times the mass of the sun and just exploded almost immediately. So we don't think Earendel, we think it's unlikely that Earendel is a population 3 star, but it might have been one of the first few generations after that.
Yeah.
And so that's something we're really excited. And maybe if Webb is lucky, we'll get some kind of data about the population 3 stars. Because as you know, these things are hard to see. They're in what we call the cosmic dark ages. And I don't know if you want to talk about that, but
sure.
That's a limit that you really can't get around even with a very powerful telescope. I mean, we're doing the best that we can, but it's sort of odd to think my cat's busy knocking things off the desk.
That's what they do.
They do, yeah.
So,
but anyway, back to cosmic dark ages. So it's amazing to think that sort of the whole universe, the universe as a whole, kind of changes the way it works. And after you had the Big Bang, things were expanding and they were cooling off so quickly that within about 400,000 years. Oh, there we go. Something's off my desk. Within about 400,000 years, he's knocking things off my desk as I speak. Within about 400,000 years, the universe had cooled so much that the universe was able to form regular atoms. There were protons and neutrons, and electrons were able to to sort of fall into orbits around them. I mean, when everything is really hot, the electrons have so much energy. They're just racing around, and they can't even fall in and feel that electromagnetic attraction between the protons and the electrons and make atoms. But all of a sudden they did, and that's great. But the problem is that once you have electrons in stable orbits, they're very good at absorbing light because you shine light through a gas that has atoms in it, and the electrons can jump up and down in their orbitals and absorb light that way. That's great, but that means the universe absorbs light very well. The gas between the stars it absorbs light, it blocks the light, and so you can't see very well at that era. But then after the first generation of stars, and this is one of the reasons why we think there must have been a party of star formation. All of a sudden, the stuff between the galaxies becomes ionized again. Something was pouring out huge amounts of energy, right? I mean, there probably were giant jets, hundreds of thousands of light years from forming star clusters, supernova explosions. So all of a sudden, the electrons get stripped away again, and voila, you can see. Everything's much more transparent. and that's called the reionization of the universe. There's probably, let's see. So here you've got the dark ages in your diagram. I'm pointing to it.
Yeah.
And so after the dark ages, you have that formation of the first stars that then heat everything up again, and now light is much more easily travel between the galaxies. So the dark ages is a time when I mean, just the universe itself was really good at absorbing light, and that's hard to see. But we're hoping that maybe some of these giant clusters of population 3 stars were sort of ionizing areas around them already, and we can see in to sort of what these stars were like. But that'll take some good luck, and I got my fingers crossed.
I was going to ask about that. So it sounds like you have to have the an appropriate galaxy cluster, and then you have to have one of these stars has to be in the correct alignment with it. So is this just a case of doing a massive survey with James Webb and Hubble and hoping, fingers crossed, to find as many of these sort of special alignments as you can find in the sky?
Well, to some degree, yes. But also, I think there are ways that the Webb telescope could study this early population of stars that don't need gravitational lensing. I mean, it wouldn't be able to actually physically resolve a single star, but it could probably see the light coming, from that time. And we might be able to see from the spectroscopy by breaking it up into a rainbow and looking at all of the different lines and elements, to see that, oh yeah, this is at least light coming from the time of the population 3 stars. So yeah, I mean, if you want to actually resolve one of these stars, then you'd have to hope for a gravitational lens. But you could study the sort of the conditions and the populations as a whole, maybe even resolve some clusters of stars at that distance, and at least be able to tell something about them. Yeah.
So people like to see the individual star, but it's not necessarily as important for getting information about that period based on the distance it is away. We can tell things without resolving individual stars. It's just nice that in this case we've managed to resolve that individual star system. Where is obviously it's not going to help you with your telescope in your back garden to see it, but what direction is Earendel in the sky if you were to sort of look out into the sky?
Oh, and that's a good question. That's something that that's something I did not look up. And to tell you the truth, I think that's a really interesting, a really interesting difference between amateur astronomers and astrophysicists, because as astrophysicists, we're sort of physicists that specialize in how stars work. We honestly don't know the night sky very well at all. If somebody goes and says, what constellation is that? I mean, if it's not one of the really well-known ones, I'm like, Auriga, Aquila. I don't know. And even worse than that, I'll go to amateur astronomy meetings, which I love. I mean, I love looking through small telescopes. I think that's great. But people think I know how to set one up. And it's like, no. I mean, I can tell you about the quantum mechanics of a stellar atmosphere, but I have no idea how to set up a telescope.
Same with me as a physicist. Like, just me, I don't touch things. Like, don't ask me to set up something scientific in your home, because that ain't gonna go well. Trust me.
Yeah. Well, why is it for some reason the constellation Taurus is standing out in my mind? And somebody might have said that. That might be a guess, but if it's wrong, I don't claim it. But yeah, you wouldn't be able to see this with your unaided eye.
No. Don't worry. I can always. This is the beauty of YouTube. You can stick a little description and a little entry in the description and clean that up. So don't worry about that. So the question becomes, I guess, what was because this is obviously an amazing achievement and an amazing new record. What was the previous record for the distance to the furthest star, and what's been overtaken basically?
Yeah, so sort of same thing. So the other one that we'd found before this, and I think the press release for this was in 2018. It was called Icarus.
Is it this one? There we go. Yes, Icarus. Yes.
Icarus. Yeah. So Icarus was, I think about we saw it. We see it as it was about 9 billion years ago. So that's how far away the previous record was. And of course, 12.9 billion years ago is a big jump from that. So I mean, and then this really has to do with what we were saying about what we call those caustic rays. Yeah. That this star happened to catch just the right part of that lens to be magnified hugely. So that was really cool. To give you an idea how common these lenses are, I mean, we now see these. The Hubble Space Telescope does surveys where it looks for these gravitational lenses. And now, I mean, and that's why it was discovered by a grad student. Now they're just given to grad students. It's like, here's a gravitational lens. See if you can see anything interesting in there. And so this really nice guy named Brian Walsh was going through this as one of his grad student projects, and he happened to see that indeed there was this pinpoint that he was able to figure out that was a star. And he's a huge J.R. Tolkien fan, and so he said he was the one that named it, and I thought that was really lovely.
Yeah, we had him on Friday. He's a really lovely and a very unassuming chap, and explained it really nicely as well. Yeah, he's a lovely chap. So some people might be confused, and I know we mentioned this before we sort of got onto the stream, that you've had a couple of nitpickers come on after you were on CNN describing this. So this star existed when, or the light that has come from the star was when it was the universe was 7% of its current age, but it isn't there now, is it? And we now see it also deeply redshifted. So could you unpack that a little bit for people, because it's not at 12.9 billion light years away now, is it? So there's a little bit of discrepancy now.
There's a couple things to unpack there. So for first of all, let's talk about, does that star exist today? And the answer is absolutely not. That star was a massive star, and so its natural lifetime was probably about 1 million years. So that star only lasted about 1 million years, that it blew up. Yeah. So it is long gone. But that star didn't live very long at all. So some people say, well, did you find the oldest star that you know of? Yes. And this is where you have to sort of make sure you've got your definitions right. There are stars nearby us in the Milky Way galaxy that are on the order of 11, 12 billion years old. They formed very soon, after stars started forming. Some of these little red dwarf stars that last forever. So we certainly know of stars that are older than the star. The star lived about a million.
Methuselah star, or
that's right, the Methuselah star. That's right, yeah. And and people sometimes kind of nitpick us, and they say, for a while the estimate for the age of these stars was actually older than the age of the universe. And no, we don't think there are stars that are older than the universe. But what you're looking at is our methods give us certain amount of error, right? I mean, we know that our methods aren't perfect, and as scientists, you have to be able to say, well, so I think it's about 12 billion years old, plus or minus 2 billion years or something, and you have to really be honest about the fact that you don't really know what exactly, your measurements can't tell you exactly how old it is. So we certainly do not think they're older than the universe, but we do think that these are very old stars, stars that did form very soon on. So it's definitely not the oldest star. And so you'll notice that I've been very carefully saying that we see the star, as the light took 12.9 billion years to get to us. For Icarus, I said we see it, the light took about 9 billion years to get to us. So the thing is, the universe is expanding, and as you see in this diagram, you have the expansion of space itself stretches out light that travels through it, and that the consequence of that, as you see, is that it changes the color. Different wavelengths are how our eye perceives color. So different energies or different colors to our eyes, and so as space stretches, as it expands, the light loses energy. The light wave gets, it starts out very intense and packed, and it gets stretched out by the expansion. And so that is the way that we actually estimate how far away these objects are, because the light, when you look at the spectrum of hydrogen, so if you take hydrogen light coming from hydrogen gas, and you break it into the rainbow, there are very specific colors that you see that it should be shining in. And then those colors are shifted toward the red end of the spectrum, and how much they're shifted gives you an idea about how much expanding space it had to travel through. Yeah. And so it's a pretty good way, if not a perfectly exact way, of estimating how long ago something left. And like you were saying, so we're not saying that it's 12.9 billion light years away, because now it's much, much farther than that. Yeah, yeah. Okay, when the light was released, coming on its way to us, it took 12.9 billion years to get to us. But that object is also expanding away from us as the universe is. And so the estimate, and this depends on assumptions we make about how the universe expanded. I mean, do we know exactly how, fast the universe expanded at different times in
Yeah,
its
yeah.
age? So this is an estimate, but the estimate now is that wherever that star, wherever the space that star is, that was in the blew up long ago, wherever that bit of space is probably now about between 23 and 24 billion light years away from us. So,
We're not going. We're not going there anytime soon. Is the upshot?
no,
Yeah.
it's very, very, very far away.
Mm.
So that's an odd thing because people say okay, well, the universe has only existed since the Big Bang about 12.8 billion years,
Mm.
and yet you're saying this thing is 20 billion light years away. And in fact, we think that the diameter of the observable universe, just the stuff that we can see in the sky, is now something a bit more than 40 billion
Mm.
light years across. Because like I said, as stuff emitted light toward us, okay, here comes the light. That's great, but that object then has moved farther away from us in that amount of time. And so yes, the universe is bigger than you would think, given the age and the speed of light. And then the limit to the observable universe is some things are so far away from us that light is expanding so much that there's so much space in between us and that object that the light will never get to us.
I'm remembering. I'm hearing a dim bell go off. A word horizon in my astronomy lectures from years ago. That we will never be able to see beyond that horizon of the observable universe.
At least you're not in any kind of conventional way. I mean, it's when people ask how big is the universe, I think that it's really understated that we have no idea. I mean, we know the observable universe is the stuff where light has had time to get to us, but there's stuff that is going through so much expanding space, its light will never get to us. There's so much space expanding between us and them that even at the speed of light, it's never going to get here. Yeah. So, there's a limit to what we can see. And I mean, that is certainly not the size of the universe, because this is an observational effect, and it's centered on us, right? It's centered on the Earth. It's like, how far can we see in that direction, in that direction, in that direction? If the universe were centered on us, I'd be really worried. I thought we gave that up a long time ago. So no, the observable universe is just how far from our perspective, our point of view, we can see until things the light can't get to us. Yeah, it's there it goes.
You mentioned that this star isn't the furthest away object that we've seen, is it? Because you mentioned you can get these smeared out galaxies. So we have seen further away in terms of whole galaxy clusters, but we've never been able to see something that is this small, because obviously there's an interplay between that resolution and the distance. So we have seen further away things that are bigger, but never seen something this small that far away. Is that a correct characterization?
Yeah, and I mean, and if you want the answer for what's the farthest away we've ever seen, that's the microwave background. So the microwave,
that makes sense. Yeah.
That's right. So the microwave background radiation is radiation from very soon after the Big Bang, about 400,000 years after the Big Bang, and it would have at the time been ultraviolet light, very sort of higher energy light, and it's been shifted down so much because of that redshift that it's now in the microwaves, and that radiation comes, like I said, from about 400,000 years after the Big Bang. That's as far as we'll ever see with a conventional telescope. Because at that point, and the reason we see that, any farther back than that, the universe was actually opaque because it was like the surface of the sun. It was so hot that you actually couldn't see any farther. And then there was a moment as this hot universe expanded, it finally became transparent to light. And then that's the moment that we see when we see the microwave background. So, if we're ever able to see farther than that, back in time, it'll probably be with something like a gravitational wave observatory. As far as light, that's as far as you can see, because then the universe is opaque. It's like, oh, okay, that's it. But there may be ways to look farther using neutrinos, using gravitational waves. But that's the farthest we can see.
That makes sense. So one question that comes up. We mentioned at the start of the discussion, Hubble and James Webb, and obviously we're going to want to keep looking at Earendel with James Webb, and I think Brian mentioned that they have some of the very, very scarce and very, very sought after time on James Webb for the start of the science running. So a question comes up as to how long will we be able to keep observing this star? Because if it's all based on alignment and having these good alignments, how long will that last? Naively, it seems that if you have such a huge circle, this thing is so far away, that alignment would stay for quite a long time. But obviously it depends on the relative distance between the galaxy and the thing that's being lensed and so on and so forth. So is there any idea as to do we need to do this quickly, or is this something that will remain observable for many years to come?
Well, I mean, I think the answer is quickly-ish. I mean, and again, this is based on just sort of, statistics and kind of what we know of how these things change. Because this thing is lined up exactly on that peak of the wave, to get that super duper magnification.
You can see the crossover, I think, in the diagram, if I find the right. I've got so many pictures, but if I can find where is it? No, I've lost it. There it is. So you can see that the maximum magnification line cuts right through the star. So if it starts wandering off too much either way, we're going to lose that sort of caustic.
Yeah, and that magnification line will also change based on the position of the galaxies and how the galaxies are lensing space. But then that star as well has some sort of motion of its own. I mean, and I know at this distance it's going to be very small, but so we don't know for sure how long this will last. But the estimate is probably some decades, but not forever. So I mean, we will have time. We hope years to observe this star. Yes, but I mean, probably in 20 or 30 years, there's a good chance that it'll be off that magnification line. So, the estimate is some decades, we don't know for sure, but not centuries.
I think Brian mentioned something about that his estimate was about 15 to 20 years, which seems to tally with what you said. So we don't have to jump on it tomorrow, but we want to take a look as soon as we can. So what would you say, just as we sort of come to the end of this then, what would you say are the biggest impacts of this finding? Is it giving us that window into understanding an earlier stage of star formation and therefore getting more information about how our universe developed from the very earliest stages? Is that the biggest implication for this finding?
Yeah, I mean anything that shows us this time when the first generation of stars was forming. I mean, even if it's a tiny little dot that we were going to do a little follow-up on, it is essential, because there are things right now in astronomy that are I mean, I don't want to call them big problems because they're intriguing challenges, but there's stuff going on at the very beginning of the universe that we don't understand at all. And I don't mean the Big Bang. I mean, we don't understand the Big Bang either, but I mean, we understand sort of what happened. We don't understand why the Big Bang happened. But the big thing that really gets us is there are these huge black holes that have formed very early on in the universe's history. And we can see them because, I mean, strangely enough, a black hole can be very, very bright. Some of the brightest stuff in the universe is the material around black holes, not the black hole itself. But if the black hole is eating a lot of stars and gas, it heats up to millions of degrees and shines with a light you can see all the way across the universe. And so we see black holes that are millions or billions of times the mass of the sun when the universe was less than 1 billion years old. And we just don't understand how you could form black holes that big, because the only way we know how to naturally form a black hole is to have a massive star explode. Yeah. Okay, great. So now you've got a black hole that's a couple times the mass of the sun. Fine. Okay, so then there's a lot of these going off together. Maybe they all come together gravitationally. The black holes all form one big black hole. Great. But how do you get millions or billions of stars to do that so quickly?
Yeah.
And this is a big mystery, because then those black holes go on to sort of, I think, become the seeds of the early galaxies. Every big galaxy seems to have a big old black hole in the middle. So
it sort of suggests that there was a huge population of super big stars to make those in the first place, is my naive first thought, right. Which I guess is the population 3 stars potentially.
So that's exactly it. And so, what were these stars like that could make these huge black holes? I mean, the universe was much denser at that time. There was more stuff to play with in terms of material. Dark matter, although it doesn't give off any light, you can't smell it or touch it or anything. It has gravity. But the dark matter was denser too. So
Yeah.
did dark matter help that those gravitational cores form and then big, star formation and black holes? So, the thing that I love actually is that, most people that know astronomy have heard that our atoms were formed in supernova and stuff like that, that anything besides hydrogen, helium has to be formed inside a star explodes. And, supernovas go off all the time and we see this happening, and that's all true. Yes, we do. But the vast majority of all of the complex atoms in the universe were formed in that first generation of stars. It's a little bit of a fudge, we tell people. It's not a lie. But yes, supernovas are still producing this stuff. But when you look back in time and you see how much of this material there was, so microwave background, nothing. Hydrogen, helium, a couple 100 million years later, basically the chemistry we have today.
Yeah.
So pretty much all of the stuff in your body was made by this first generation of stars. And, that's mind blowing.
So we owe them a lot, basically, without knowing too much about them at the current time.
Yeah. So I mean, Earendel has a lot to teach us. I'll show you. We're all Tolkien fans. I got my Elvish. I got my Elvish tattoos there.
Nice.
So yeah. So I'm really happy that they got a little Tolkien in there. And it was just a wonderful discovery, and it was really, I got a chance to coach Brian a little bit for doing some of his interviews. He, really nice person, and I'm very fortunate part of his PhD dissertation.
Yeah, he's a really lovely chap. So I'm very grateful he took the time on Friday, and I'm really happy that it's getting such great reception, and people are looking at his work, which is amazing. Do you have another 10 minutes? Because I wanted to change tack slightly and just talk about your scientific communication, but I'm mindful not to take up too much of your time. Okay, excellent. So you are the Assistant Director for Science Communications with NASA, which sounds like an incredible dream job for many science communicators. Why is it such an important role, and what's kind of your role in NASA to getting science to the public?
It's funny. I mean, like everybody else, a lot of my role is kind of administrative. Like coming up with writing some policy documents and working on budgets and schedules and all of that. I mean, then lots and lots of meetings. But it's an interesting job because it's a job that I kind of define for myself. And that can make for a really cool career. It can also make for a lot of insecurity because you're never really sure where you fit into an organization. So I started out as a postdoc at Caltech, and I started working on the Spitzer Space Telescope. And at that time, NASA decided that they wanted to get really serious about communication, to sort of get the public more involved, make sure it was being done well. And so they required all missions to spend 2% of their total budget on education, outreach, something. And that had never been a requirement before. And all of a sudden there had to be like formal plans, and budgets, and who's going to do this, and what are we going to do, and how are we going to measure our success, and all of that. And nobody had really done that formally before at NASA. Nobody had done it in that way. And so it kind of got thrown to me, a postdoc. They were like, hey, you're a postdoc. You kind of like talking to the public. Why don't you figure this out? And for the Spitzer mission, that turned out to be, a multi-million-dollar budget. And I didn't know what I was doing. I'd never done any of that before. I just basically failed until it was okay. They said, okay, you've stopped failing. But I thought it was very important that to have the public, and I really don't like the idea that when you talk to the public, you're dumbing things down. If you can say things simply and sort of in this elegant way, if you can find the narrative, the story in this science result, people really do respond to it. My mother is quite. I have tried to teach her what causes the moon phases a dozen times. I get little balls and a flashlight, and I try to show her, and she just can't. She's just like, I don't care. I don't want to know this. I don't. But I was talking to her last week, and she knew about this result, and I hadn't told her. I was just like, wow, that's amazing. These days at NASA, we have social media accounts that have hundreds of millions of followers, and we're able to reach the public in a much more personal, kind of one-on-one way than I think we ever had. So I thought that this was a tremendously important thing. And I also think it was what I was good at. I mean, I think that honestly, I would have been like a decent run-of-the-mill research astrophysicist. It's not that I.
It's so funny because I say exactly the same thing. I say when I was at CERN, I was like, I must have been smart, I must have been good, but I was in the very much in the middle of the pack but I was like, this was the thing that I really enjoyed doing. So it's really interesting to hear you say that as well.
Exactly. So I mean, I was never going to be a star astrophysicist. That's a strange thing to say, but you know, and I also just liked it. I liked this work better, and I thought I was better at it than I was at research science. And so that was fun. You know, I love my job. I love the people I work with. I love the people at NASA. The thing that kind of career gives you, and you probably are familiar with this, is the insecurity of, am I doing this right? How do I fit into the organization? Am I ever going to get promoted?
You want to see all the sheets on my desk that say, plan for tomorrow. What am I doing? What are the goals? Because there's nobody there to kick my ass if I don't do something. Right. So I have to be on top of what's going on myself. And that is very, very tricky sometimes.
And you don't know if you're doing it right. You know, it's like is that enough work? Is that not? You know, I mean, because you don't really have the goalposts that other jobs do. And so, you know, I mean, it's been a wonderful career, if sometimes insecurity inducing. And then, you know, I'm thinking about wrapping it up relatively soon, retiring, you know, reasonably soon. And definitely just doing sort of the same thing, but maybe more on a volunteer basis, or you know, maybe teaching some classes on science communication. Because after working with scientists as one of them for decades, I kind of know sort of exactly where they trip themselves up. And I know some of the, you know, and I have so much sympathy for them. You know, I know how they've been trained to talk about this. And you know, I remember when I used to give, you know, public presentations, and I would show high schoolers a Hertzsprung-Russell diagram because it's so clear. It's so wonderful. Look at this diagram. It shows you the different stellar. And it's like, what the hell are you doing? You know, scientists can look at a graph and go, that's the best way to present that. That's so clear. Look at that. And everybody else in the world goes, it's squiggly lines. Great.
I remember when I was at Cambridge, we had fourth year lectures in the maths department. And we had a very famous string theorist, very I won't mention his name because, you know, there's a few, just to save his embarrassment. Not that he'll really care about this, but he was the worst lecturer I've ever had. And the reason was not because of his intelligence or his ability. It was because he couldn't understand why people didn't understand it immediately when he was just scrawling everything all over the board. And even the brightest mathematicians in Cambridge were like, his lectures are just awful. Like, I have to go get the book and try and understand what's going on. And then the best lecturers I had were some of the ones who had come from less prestigious universities that quite struggled to understand it potentially themselves. And their notes were just so much better. And the way that they presented the difficult topics was so much better. And as you say, you can get that disconnect just because a scientist looks at it and goes, that's incredibly clear. To my peers, that's going to be awesome. But then when you're explaining it to someone who hasn't had that formal training in the field, you've really got to not dumb it down, but change the way that you bring things to them and the ways in which you explain it.
Well, and also the assumption of knowledge. I mean, seriously, heliophysicists drive me nuts because I love heliophysics, but I mean, I swear they don't remember a time when they couldn't do a triple integral. Because you know, I have been at I've been at seminars at Goddard where they're supposed to be like general science seminars, and there's been a PowerPoint slide with a triple integral, and I'm like, I'm not going to do a triple integral on a PowerPoint slide. You know, I mean, it's not going to happen. And so, you know, one of the things that I do, this is an exercise, and this is all the people are helping me with this. I'm very well coached. They feel very safe. It's not about making them feel dumb, but I take people from our procurement department and our legal department, you know, people that are experts, that know NASA, that have worked at Goddard for years. And I basically give them, like in football, I give them a yellow card and a red card. And so I'll have a scientist sit in front of them and start explaining their research. And then they're supposed to start, you know, and they know this is not about them being dumb, but they start holding up a yellow card when they're not quite sure what they're saying. And then when the scientists have lost them, they hold up the red card. And the scientists are shocked that, you know, somebody who works in the procurement department might not know the difference between a comet and an asteroid. or they might not know what are there other galaxies, and or look at this triple integral, and so it really it kind of blows their mind when they realize that people working next to them, who they know are very smart, that mission would have gotten funded if that financial person hadn't done that budget right. It's not general public knowledge, how many quarks there are.
Yeah.
I always said I would never date a guy unless they could name all the quarks. But I mean, generally, that's not.
As long as they've got plenty of charm and beauty, you're away.
We won't even get into top and bottom.
Yeah, good catch. Yes.
Anyway. So yeah, so I mean, the idea that science communication is something that really required some focus and somebody to really look at it and look at what was going wrong, and so I love doing the press releases and the public stuff. That's a very small part of my job. The biggest part of my job is reading press releases, vetting things, training scientists, working on the schedules of what's coming out.
I'm guessing there's a lot of internal stuff in NASA as well, right? Because you have all these big separate departments that probably, if it's anything like any other scientific institution, don't talk properly to each other at any time when they really should. So I imagine there's also an inward-looking part as well as an outward-looking part. Is that fair?
Oh, absolutely. I mean, most of the training that I do, I'm training other NASA scientists, right? So there's lots and lots of that. And then there's lots of just trying to, be strategic. So if we have a press release coming out, what's our social media plan? How are we reaching the television audience? How are we reaching the radio audience? What are we doing to sort of amplify this effect? And then tracking that, and showing, okay, well, this worked better than that because we got a better response rate. Yeah. So there's lots and lots of work to be done inside the organization. And I mean, and just Goddard. So NASA has 10 bases around the United States. Goddard's one of them. And Goddard has about 10,000 people. And so about 2,000 of those people are PhD scientists. So that actually makes it the biggest space science department in the world. And there's nowhere else you have 2,000 space scientists. And then we have a huge number of engineers. I mean, more engineers than scientists that are actually building and testing and developing some of these new technologies. So even just inside one NASA center, there's maybe 60 people doing outreach and communications. And we want to make sure our press releases don't come out on the same day. We don't want to step on our own story. We want to make sure they're all supported. We did this huge interview campaign about this Hubble result last week. That, of course, was organized. We had to write all of the questions. We had to contact all the stations. I mean, all of that takes a lot of organization. And but it's something that I still feel is very important. And it's still actually kind of fun after nearly 25 years.
I'll tell you, because we've got on so well, I'll tell you my Caltech story, because you mentioned Caltech. So I went there on a sort of astronomy sort of outreach program, actually, after my first year in Cambridge. It's called Curia or something like that. I can't remember the exact name, but it was up at Mount Wilson. And it was really cool. And then one day we went down to Caltech and we had a sort of dinner, and they showed us around. They were like, we're going to have a guest lecture and it's all going to be great and awesome. We're walking down the corridor, and a gentleman sort of presents himself, and he's like, "Hi, I'm Kip Thorne," and I had no idea who this was because I hadn't done any astronomy and stuff at this rate. It's first year. I was just like, "Hi, I'm Sam Gregson," and he gave me the dirtiest look I've ever seen in my life, because obviously, like, I was supposed to know who this person was, and I just had no clue. I was just like, this is just a nice guy who's going to show us around. So anyway, everything sort of calms down. We go into the guest lecture. Obviously, the guest lecturer is this guy. Walks out, just gives me the dirtiest look in the front row that I've ever had. And I was like, I have no idea who this guy is. And then Google afterwards, I was like, oh my God. Like,
but that's never acceptable.
He was being a bit of a tit. But at the same time, I was like,
so okay, so yeah, Kip Thorne has a Nobel Prize now. So I instead of talking trash about Kip, I mean, I'll compare it. One of the people I work with very often that has a Nobel Prize is John Mather, and he's actually the senior project scientist on Webb. and he is one of the humblest people I know. I mean, you never want to. He never wants to admit he has a Nobel Prize, and whenever he does, he always says, it's our Nobel Prize, because he got it as a as the lead of a NASA mission that hundreds of people were to support. And I mean, the gravitational wave stuff that Kip does is incredible.
Yeah.
I mean, and not only that, the perseverance that he kept saying for decades, we're going to be able to do this. When again, skeptical, I was like, no, you're never going to be able to actually measure a gravitational wave. Yeah, they did many times now. So he's brilliant. I mean, I think that's where science communication starts to break down. When we put ourselves up on a pedestal and we assume people should know. I mean, I kind of had the opposite that happened to me yesterday at the Baltimore Symphony Orchestra, where they were doing the space-themed concert, and they asked me to come and comment on the music between each piece. And they were expecting about 700 people to come, but they got 1,100, and a lot of them wanted to come and meet me both before and afterwards. Like I told you, I'm completely shagged out after a long squat. And and then the symphony orchestra, I've been rehearsing with them, and it's just like, hey, I'm Michelle, I'm from NASA, and then about halfway through the event, they're like, who are you? And it's like, oh, I do some TV stuff, some people, I mean, it's always a nicer surprise when people realize that you're approachable and you're interested in talking to them. And, I mean, every single person is the universe looking at itself through unique eyes. And, the universe is never going to get a chance to see through that person's eyes again. We're all these little bits of space dust that randomly become conscious and then blink out again. And you might as well be in wonder about all of these other little co-creations of the universe. And kindness is where it all starts.
That's a really lovely sentiment. So as I sort of let you go then, so quick fire round. You're the assistant director. What's the director like? Are we allowed to say?
It's an odd title. It's assistant director of science for communications. So our director of science is a man named Mark Clampin, and he's wonderful. He's British as well, English. He's worked for, again, many decades on the Hubble Space Telescope and Webb as well. And I know that he's done some of the stuff. He did some of the stuff with the star Fomalhaut, where they thought they found that image of a planet around it. So that's some of the work that he does. He's a wonderful scientific leader. I don't think he'd mind me saying that he sometimes comes across a little bit cold and formal. I mean, I went to one of the lectures he gave when he first became our director of science, and he talked about how he really grew up, kind of largely in the British military. His father was a high-ranking member of the Navy, and I was like, okay, that kind of explains it. So he has all of these wonderful and very, very robust and funny women on his science team. And in meetings, we're all usually kind of laughing and telling, jokes and wondering where the champagne is. And Mark's kind of standing in a corner, And so he inspires me a lot, and he is an incredible leader. He's you'd probably recognize the type, kind of little stiff British.
Good stuff. So who is your favorite science communicator of all time, living or dead?
Oh, so the reason I'm here is Carl Sagan, right? I mean, we all have to say that.
Yeah, he's fantastic, wasn't he?
Carl Sagan's show. Yeah, I mean, I never met him. I always wished I would have. So he died, when he was relatively young, and in his early 60s. Yeah, sad. And it was very sad. I was 10 years old when his show Cosmos came out, and I'd already liked space. I mean, I already knew that I liked the stars. But then when he started telling these stories about, in order to bake an apple pie, you must first invent the universe, and the story of how the stars affect us and the history. And again, the narrative. I mean, to me, astronomy is the best stories ever told. Yeah. And I couldn't get them out of my head. And they're not equations. I mean, the equations are great. I mean, when you learn to read the language of the math, you realize that the equations are the simplest way to put something.
But they're so awe-inspiring, human interest, where we came from, why are we here? All those big questions you can sort of feed into these findings of astronomy. They're so quickly relatable to those big questions. And
something bigger than yourself, and you end up saving yourself. You end up saving your life through this. I mean, I saw that I had elvish tattoos. So I mean, I think since we're talking a bit about lives and how we respond to astronomy, so my husband was this brilliant engineer on Webb. He got terminal cancer in 2020, and died very quickly, and he wasn't able to see the launch of Webb, and so I was on TV covering tests, and in some cases looking at footage of people in bunny suits that included my dead husband, and I would run into the room and cry a little bit, and then I'd go back out and cover it. And but the idea of the questions that we asked together and the fun that we had together, and when your most loved person in the world is dying, and you say, Ad Astra, Stardust, I'm going to be behind you really soon, and we don't even know what time and space is. I mean, when you're able to have that something larger than you to get you through that, and the curiosity and the joy. I can't imagine how I would have survived the last 2 years without inspiration in my life and curiosity. When I had nothing else, when it was all dark, I realized I was still curious. I still wanted to read that next press release. I still wanted to know what we were finding out about Mars or about, distant galaxies. And, if you're going to get through life, you need to have that foundation of curiosity and joy. And I am so grateful for that. And so what this gives us, this larger than life perspective, I found very helpful. And yeah, so the tattoo, he wrote a goodbye letter for me, and we are that geeky, Olympic level geekiness.
Nothing wrong with that.
And yeah, so he wrote the goodbye letter, and he was able to see the tattoo, and before he passed. And so now I take it with me while I talk about the Webb and the new findings of Hubble.
Well, I'm very sorry to hear about what happened, but I think that's a very positive and inspiring perspective to take. So I think that's a really nice place to leave this. And I thank you so much for taking your time this morning. I've really enjoyed the discussion. Just the topics that we've discussed, just the energy of the discussion, and I hope everyone else out there has enjoyed it as well. Is there anywhere that you'd like to point people to find out more about what's going on at NASA, and just to keep up with all of the amazing projects and keep that curiosity going, I guess?
I think sometimes a lot of people don't know about the really good thematic websites we have. I mean, there's the main NASA.gov website, but that one covers like everything from the astronauts to the space station. There's some really good ones that cover more of the science stuff. Like there's one called exoplanet.nasa.gov, which gives you all of the latest stuff about all the new exoplanet discoveries. And then there's one called climate.nasa.gov, which is all about the Earth science and the changing Earth and the climate change.
We had a chat with Gavin.
Gavin Schmidt.
Yeah, Gavin Schmidt. That was really good. So yeah, we know about that one. Yeah.
Yeah. So there's really good thematic ones. So you might actually find it more easy to find stuff on these ones. They're ones that are more dedicated to Webb or to Hubble. Then there's Mars.nasa.gov. So I mean, there's some really cool stuff going on, and the stuff coming up soon with exoplanets and Webb knowing whether they have atmospheres like the Earth, detection of a possible biomarker in the atmosphere of Venus.
Yeah.
I mean, all of these cool things that are going on.
I chatted to Sarah Seeger about that one, I think, but I don't know if that one is still. I remember there was some pushback on that, and then it sort of went dark. I don't know what the status on that is at the moment. I need to take another look. But yes, very.
So it basically, like any good science, it swings back and forth. So they saw something a while ago. They thought was this molecule phosphine. Then they're like, well, no, maybe not. Then ALMA sees it, and they're like, well, okay, ALMA saw it. Well, but did we? So I mean, in order to just put it to bed, we actually are building a lander to land on Venus called Da Vinci. And Da Vinci will have a specialized camera looking for that phosphine. Amazing. Up close. It's like, there it is, right in front of us. Seriously, the molecule's like right here. And so, that'll hopefully put to bed. And if it is phosphine, that's very interesting, because we don't know how to make phosphine without life.
Very interesting. Lionel's popped up in the chat and says, apparently, according to Wikipedia, because obviously that's the greatest source on Earth, Earendel is in Cetus, apparently. So
thank you.
There we go. So Thank you very much for that, Lionel. Sin Cetus.
I do know Cetus is a whale. I know that much. I know that Cetus is supposed to be like a whale shape on it.
Awesome. And that's how science works. We can all collaborate and we can work together and we can all be curious together. So, Dr. Thaller, again, thank you so much for taking the time. I will get back in contact with you about this potential Biggie Smalls podcast that we might run. I'll be the Smalls doing the particles. You can be the Biggie doing the astronomy. I'll also work out this movie that you mentioned that I wasn't quite sure what it was, but it sounds.
Oh, but Pootie Tang. We were talking about Biggie Smalls,
that's right.
That's the name of the character in a movie called Pootie Tang that starred Chris Rock. Yeah. But yeah, the other thing is, I don't know if you've ever seen the podcast Drunk History, where people get drunk and then try to explain history, and it's hilarious. I mean, it is. I have laughed myself silly on some of those. I think we should do like maybe drunk astrophysicists, where it's like, okay, so explain the Gunn-Peterson effect. After 3 scotches.
Absolutely no objection to this. This sounds like an excellent idea.
It's like Gunn-Peterson happened when atoms did this, and so.
I'm down for this. We should discuss this. I'm up for that. Good stuff. They sound like great ideas. So I will let you go because I don't want to keep you. We've already kept you for an hour and a quarter. Again, really appreciate you taking the time. Let's stay in contact, and hopefully when the next big thing comes down the pipe, we can get you back and we can have another chat.
I'm here. All good.
Thank you very much for taking the time, and I'll talk to you soon.
Thanks a lot, Sam.
Bye now. Bye.
Bye.
I ended the stream. I've got to do the sort of sign off.